I want to begin by putting this work in the context of my PhD thesis to illustrate why I'm interested in resolution of abstract anaphors. So at NACL this year, I presented a sentence-level opinion analysis model that is able to detect from this sentence, we therefore as MDMC do not accept this result, that MDMC expressed some kind of negative attitude towards the opinion target, which is in this case some kind of result. It's very abstract. And having all this information probably is not very useful for you because you still have no idea what MDMC is really negative about. So we can't look at these sentences in isolation. We need to go beyond this sentence level in Discourse, in the two previous paragraphs, and find out what this target is about. So if you read this paragraph very quickly, you would realize that the result refers to the fact that Mugabe was re-elected with certain amounts of vote against its opponent, Tsvangirai. And now you have much more meaningful piece of information. Now you're able to say that MDMC is negative towards this election result in Zimbabwe. But we don't need to necessarily stop here. Now as humans, you probably, even without realizing, you inferred even more. You inferred what is not said but is implied, and that is that if MDMC is negative towards Mugabe being re-elected, then they are probably negative toward Mugabe, the person who is being elected, and positive toward the person who is not being re-elected, and that's Tsvangirai. So once we have made this inference step, we have much better and deeper understanding of subjective language because we do not explicitly focus on what is explicitly said in this text, but we are detecting implicit opinion as well. And these implicit opinions are in the very core nature of subjective language. However, computationally modeling this inference step is hard because it involves an interplay of some challenging subtasks. You need to find out who explicitly expressed what kind of attitude towards who or what. You need to resolve anaphors that refers to fact, events, situations, and so on. And you need to resolve noun phrases that refer to a concrete objects in the real world, like that MDMC is an organization, and that it's a reference in this text with the pronoun we. And finally, when you have all these three steps covered, you can propagate sentiment in discourse beyond one sentence, and you can find out that MDMC is negative toward Mugabe and positive towards Tsvangirai. And probably you already realized that, given the title of my talk, today I will talk about the second step about resolution of anaphors that refer to facts, events, situation, or properties. So let's get more concrete here. Abstract anaphora resolution is a task of finding the antecedent of nominal expressions, such as this result, and pronominal expressions, such as simple pronouns like this, that, it, that refer to so-called abstract object antecedent in some of previous sentences. And these abstract object antecedents are facts, events, situations, properties of something. So if it's too much now this Monday morning to figure out all these new linguistic terms, you can think about this anaphor as either noun or a pronoun, but highly abstract, that refers to a clause in the preceding context.
Quick question. So are you excluding anaphoric expressions like the president that refer to people?
Yes, yes. So in this work, we are pretending like someone told us this noun phrase or pronoun is abstract, and then we try to find the antecedent. Of course, more full work would first detect whether the expression is abstract or individual. Okay, so I guess more of you are familiar with entity-anaphora resolution or coreference resolution, which tries to resolve multiple ambiguous mentions of a single entity that represents a location, an organization, or a person, like that MDMC is referenced to the pronoun we here. So why is the case that abstract anaphora resolution is relatively unexplored, although abstract anaphors are frequently occurring across many languages? Well, there are at least two reasons. One is that standard features such as saliency, agreement, apposition cannot be applied for anaphora and for abstract anaphora resolution. And another major reason is that there are considerable amounts of labeled training data for coreference resolution, whereas we don't have any training data for unrestricted abstract anaphora resolution. Yeah.
When you say they occur frequently, can you give me a sense of how frequently, or maybe compared with entity-anaphoric?
In the next slide, I will have few references, and these are papers which give numbers, but I can't remember exactly. I would say roughly 20%, but I need to check these papers. Okay, so in the EMNLP paper last year, we proposed a neural model that can learn these relevant features from data alone. And to train such a data-hungry model, we proposed a method that extracts training data using a single common syntactic pattern. However, I want to stop here and just emphasize that even with sufficient amount of labeled data, unrestricted abstract anaphora is a difficult task because antecedents vary in size, in syntactic type, in distance from the anaphor, and there is no one-to-one relation between the antecedent syntactic type and anaphor semantics type. And even we as humans do not generally agree on the exact boundaries of the antecedent. So here we have different references. Some of them are for Danish, some are for German. Okay, so it's given that this is a difficult task, it's not so surprising that the NLP community kind of focused on different aspects of this task. And the most prominent example is event coreference. For event coreference, a system needs to detect which mentions refer to a same real-world event. So here you have head hang and suicide, which both refer to the same event of Lord Preston killing himself. Such systems can be trained on relatively large amounts of training data. However, there is a major difference between event coreference and unrestricted abstract anaphora resolution, and that is that event coreference usually deals with a verb and noun phrases of similar abstractness levels. So here you have hang and suicide, whereas abstract anaphora resolution involves really abstract noun or a simple pronoun that refers to a clause in the preceding discourse. More relevant is what I call abstract event resolution, and here a system needs to find the antecedent of an event which is referenced by a simple pronoun, which is highly abstract. So here you have this, and this refers to a verb phrase antecedent plummet much further than a local economy in recession. Jahar and colleagues trained a feature-based model on a subset of the Colon 2012 shared task, and this subset takes all pronouns whose preceding mention in the coreference cluster is a verb phrase. Another related task is sleuthing. Sleuthing is an elliptical process whereby the majority of question goes unpronounced as long as there is a salient antecedent to recover it from in the previous sentences. So here you can understand that the complementizer of this VH phrase why is understood to be why he resorted to do that. Anand and Had proposed a feature-based model on the data they collected, and Roning this year proposed the first neural approach to sleuthing. Stetter and Grishina, they investigated anaphoric connectives, such as therefore here, which pick up the abstract object antecedent in the previous sentence, and at the same time signal the relation between this antecedent and the host clause. But they found out that these connectives are really restricted in type and require word sense disambiguation. And finally, the most related to our work is work by Kohatar, Zinsmeister, and Hurst on resolving 6 highly abstract nouns, which they call shell nouns, such as this issue here. And they proposed a clever method to extract training data, but unfortunately this method heavily exploits the categorization of shell nouns in literature. So it cannot be directly applied to unrestricted abstract anaphora resolution. So what I want you to remember from this table is that there is some work on certain types of abstract anaphors, but they are always pronominal or nominal, never both. And data for abstract anaphora resolution is really scarce for both training and evaluation. So what we have done in the last year's CMNLP paper, we proposed a method that deals with the nominal cases as in the first example I gave you, but with pronominal cases as this one here. And we as well extracted training data using some automatic method. and we evaluated our model on the subset of the oral corpus and proposed first results on this subset. Okay, so I think so far it's clear that our goal is a unified approach for abstract anaphora resolution, and by unrestricted I mean that we don't make any assumption on the type of abstract anaphor. And the question is, of course, how can we learn what is the correct antecedent for a given abstract anaphor? And our intuition is that we can learn that by learning the characteristics of the relation between the anaphoric sentence where the abstract anaphor occurs in, and the antecedent. And in the first example I gave you, these characteristics would be characteristics of something MDMC may not accept. I will go into details of the model, of course. However, you remember from a few slides ago that we really don't have training data to train such a model. But luckily for us, if we collect many anaphoric sentence antecedent pairs, we can train such a model. And luckily, such pairs can be extracted from parsed corpora if you look for a construction which involves a verb phrase with an embedded sentence. So here you have that, do not accept, and the embedded sentence is Mugabe was re-elected, blah, blah, blah. And you make a simple transformation. You replace this embedded sentence, and you take it out and replace it with a suitable anaphor, this or this result in here. I will get into details of this method soon, but now I want to just stop to walk you through the rest of this talk. So as I said, we will go into details of this method. I will show you what kind of model we train on this data, and this will cover what we have done for the EMNLP paper. And then we will move on our ongoing work. We will have a closer look at this data we have extracted, and then we will cover some ongoing challenges. Any questions so far? Okay, so let's move to the training data. As I said, our work is highly motivated by the work on resolution of shell noun by Kolhatar and collaborators. And they distinguish two types of shell nouns. One is anaphoric shell nouns, whose antecedent occurs anywhere in the prior discourse. And the other type is cataphoric shell nouns, whose antecedent occurs in the same sentence as the shell noun in the position following the shell noun. So antecedent is a bit misleading here. And the huge difference between these two is that the antecedent of cataphoric shell nouns, this here, can be resolved using, can be extracted using a simple predefined syntactic rules. So you can use these syntactic rules to extract antecedent from the sentence and use the remnant of the sentence as the sentence where the shell noun occurs in. So Kolhatar and collaborators did exactly that on New York Times corpus, and they collected these pairs. And then they trained a feature-based ranking SVM model, which has to rank the extracted antecedent with a rank number 1, and all other sub-constituents of the sum context in any order. And now you might wonder, well, why would we want to do that if we can just use these rules to extract the antecedent? Idea is that cataphoric shell nouns and anaphoric shell nouns share some linguistic knowledge. So you can train this SVM to find the antecedent of cataphoric shell noun and use it off the shelf for anaphoric cases as well. And nowadays this is something we will call zero-shot learning or incidental supervision or whatnot. So in our work we extend this approach to replace these syntactic rules, which are based on categorization of shell nouns in literature, with a single common syntactic construction. And then we train, instead of training a feature-based model, we train a neural model which is able to detect features we probably wouldn't come up with in the first place.
Sorry, could you please explain again why rule-based things or these rules do not work for cataphoric?
So these rules work for cataphoric shell nouns. Yes, so you use these rules to extract the antecedent of cataphoric shell noun, of this example here. But this is not the case we are interested in. We are interested in these anaphoric cases here.
Okay, so if rules can be used for both cases, again, like, reiterating the question you asked,
Yeah.
Why can't we use rules for both cases?
They can't be used for anaphoric cases.
Oh, they cannot be used for
Yeah, they can only be used for cataphoric cases because they are always in this position following the shall noun. And here you can have the antecedent many sentences away.
I see. Okay, thank you.
Okay. So, which kind of pattern did we use to extract our data? So we used a single common construction which involves a word phrase such as doubts here and the embedded sentence, a Bismarckian superstaple, emerge, blah, blah, blah. And then you have a table here. We look at this complementizer, which is in this case empty. We go to our table, find the value of empty complementizer in the second column and the first row, and then in the third column we check what are possible anaphoric phrases. We can choose this, that, it. We randomly chose this. Then what we do is we extract this embedded sentence, we take it out, and replace it with this suitable anaphor which we chose, and it was this. So in the end what you get, he doubts this, but warns of blah, 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 where this refers to a Bismarckian superstaple emerge that would dominate Europe. So this holds for complements, but for adjuncts as well. So here you have as a word phrase cell, and you have there S as the head of the S-bar clause. You'll find the value of S in the third row, second column. And then in the third column, you check what are possible anaphoric phrases, and we randomly choose because of this. We take out this embedded sentence and replace it with a suitable anaphoric phrase, which we chose, that is because of this. And in the end, we have these firms will sell even more munis because of this, where this refers to they scramble to raise cash to pay claims related to cubic and Hugo, and so on. So again, we get this naturally occurring pair. So we harvested this data for unrestricted abstract Anaphora Resolution, just using a single common syntactic construction, a verb with an embedded sentence, and we extracted what we think of as a large-scale data for this task. That is only like 15,000 instances from the works in journal part of Pentry Bank. But much more can be extracted as long as you have an accurate parser and corpora. You can extract as many as you want. Okay, and this extraction data is what our student researchers have done, Leopold and Julia. Moving now to our model, I just want to briefly remind you on what are our intuitions. We said we can learn what is the correct antecedent for a given abstract anaphor if we learn the relation between the anaphoric sentence and the antecedent.
Sorry to interrupt, just a quick question about a detail. So when you mentioned in the previous slide that it's silver data, is that limited recall, or is also noise? I guess you mentioned in the abstract there's noise in the data.
Yes, I will have a huge part on the noise part. We thought so far that this data is not noisy. We thought this extraction was fine, but then we find out it's actually noisy, and I will talk about that. Okay, so model. As an input to our model, we give a candidate for an antecedent, which is a sub-constituent of some context. And we give it an anaphoric sentence, that is the sentence when the anaphor occurs in. We plug this into an LSTM, followed by a feed-forward layer, and we get a representation of the candidate and the anaphoric sentence. And because we apply the same parameters, these representations live in the shared space. This is this Siamese part. And this is great because now, although we can't interpret these dimensions, we can compare them. So you can get the joint representation by just doing a simple mathematics, an element-wise difference, element-wise product, put it again into some feed-forward layer for expressivity, and get a joint representation of this candidate anaphoric sentence. And our intuition is that here, in this dense representation, live these characteristics of the relation between this candidate and anaphoric sentence. So something MDMC may not accept. And on the basis of this joint representation, you calculate one scalar, one real value, which tells you how relevant, how related is the current candidate for the anaphoric sentence. We train everything with max margin objective, which was used by Clark and Manning in 2015 for their entity core reference paper too. So usually as the input to LSTM, we have only a token embedded, right? But here we concatenate more because in the anaphoric sentence, we might have more than 2 abstract anaphors, and they might have the same surface form. We concatenate the embedding of the head of the anaphor and the continuous back-of-word representation of the context of the anaphor. And because we know that some candidates, some constituents are more likely, for example, S constituents and VP constituents than NP constituents, we concatenate the embedding of the constituent tag label, which we train during.
So is your candidate generation, is it all NPs and S's? Is it?
We follow the prior work on shell-noun resolution, and we take all sub-constituents. In the ongoing work, we only take S-like, so S, VP, root, S1. Okay, so in the paper we have we did 2 sets of experiments. One was to compare our model with the shell-noun resolution of Kolhatar and collaborators. So train and test data here is taken from them. This train data is this cataphoric shell-noun pairs I mentioned, and test data they collected with the crowd workers. And here we train 6 different ranking models for 6 different shell-nouns following this prior setup. And we evaluate everything in a super restricted task setup. So here candidates are all sub-constituents, but from only one sentence, and this is the sentence where the antecedent occurs in. So this is not how you would tackle this problem in while. However, in the paper we compare to them, and in the ongoing work we are moving to this more realistic setup where you take all these sentences in between.
So are there thousands of sub-constituents in this setup, or is it a small number?
If you take sub-constituents from one sentence, it's maybe 30-ish. And then when you take from all, from 4 preceding sentences, it gets like 100.
Okay. So it's assuming the parse is correct.
Yes.
Okay.
Yeah. Okay. So here we have in blue our model, in orange Kolhatar's model, and in gray the baseline we propose, which randomly chooses a candidate with a tag in S, VP, root, or S bar. Our evaluation measure is adapted from the prior work. So it's a success at 1, which measures whether the antecedent or a candidate that differs in one word is in the first N ranked candidates. So success at 1 is precision. And the outcome is that when we tune our hyperparameters, we are well beyond these baselines in this restricted set. For unrestricted abstract Anaphora resolution, we use as a training data we have extracted, the silver data, and as a test data, a small-scale subset of the ARA corpus restricted to abstract anaphors. So this corpus has can be used for general reference resolution, but it has this abstract anaphor types as well. And it's only 600 examples, so you can't really use it for training, and it's even small for evaluation. This is still in this restricted task setup, and I want to emphasize here that our training data is pronominal silver, our dev data is nominal gold, and our test data is pronominal and nominal and gold, which is really troublesome because you have this really hard task, and you have a really hard machine learning setup as well, where you have data distribution shift, but even in 2 ways. So debugging becomes exponentially hard here.
The training data is for Wall Street Journal. You said the
Yes.
corpus comes from what kind of data?
Newswire.
Do you have gold syntax for?
Yes, so in ongoing work, we use the gold parse from Wall Street Journal, and then we parsed, not parsed, but we use automatic parse of the New York Times corpus to extract more instances. Yes. And I will explain why we use this gold as well. Okay, so here baselines are again this tag baseline in yellow, and we have preceding sentence baseline, which takes the whole preceding sentence as the antecedent. And in the paper, we show there is a variant of our model with these ablations of the architecture, which is better than the simple baseline for nominal part of our corpus, but not for pronominal part when you compare it with the super simple tag baseline. And I want to stop here and just walk you through what we have seen so far and raise some questions and concerns regarding these results. So we have made the first step toward our goal. We have proposed a neural mention ranking model that once it's trained on this training data we collected, can outperform prior work in noun resolution, and it can beat simple baselines for the nominal part of the RO corpus. However, we have seen that for pronominal cases, we are still behind the super simple baseline. And not only that, but these results for nominal and pronominal cases are way off. So we are much better for the nominal part. So the questions we raise in the papers are, should nominal and pronominal anaphors be learned independently? Because we have this huge difference in results. And if so, this is super inconvenient because our holy goal is to have one approach for all abstract anaphora types. But somehow it's very weird that our pronominal data is much better for nominal goal data. And this made us wonder, like, what's going on with our data? Is it correct or not? We haven't said anything about the quality. And the final outcome could be, well, our data is fine, but just the pronominal cases we have extracted are much different from pronominal cases occurs in quality. So in our ongoing work, we will try to address some of these questions. The first thing we have done is to have a closer look at our training data. So this is the table you have already seen, and what we have done is we sampled 10 examples per head of the S-bar clause. So for that 10 examples, this 10 examples, and so on. And two curators rated the quality of constructed data as sound, not sound, or marginally sound due to unnatural sounding anaphora or weird position in the sentence. So sometimes we put it in the end, whereas you would probably use it in the beginning and so on. And we have found that once you have these matches, once you find in these parsed corpora these constructions, you have to be really picky what can go further to make this simple transformation. So we had a lot of noise. First thing is we had to filter all matches whose embedded clause is introduced by VH phrases. Then we had to eliminate a lot of relative clauses, and a heuristic we have found to be kind of working is that we say if the head of the S-bar clause is that, and the verb phrase has more than 2 children, that's probably a relative clause. So one example is here. Then we realized we have to be much more cautious with since, as, and if, which can have both causal and temporal sense. And luckily for us, this gold parse University journal has these special markers which tell you the sense of since, as, and if. However, once you move to automatic parse, you don't have these markers, so you can't use them. We realize we have to be more cautious with whether. So once you have this coordination or, it doesn't make sense to make transformation from that. And finally, while often results with contrastive reading, I realized we could use some kind of discourse markers. So for example, here you could say, at the same time, Kellogg's current share is believed to be slightly under 40%, where time refers to General Mills' share is about 27%, but then that gets super complicated, so we drop it one. Okay, so we filtered all these unwanted matches. We added 2 new replacement types, after and until, to have more of these temporal cases. And we repeated this whole evaluation again, and we found that until very often results with antecedent and anaphoric phrase which don't really match in tense. I have a backup slide if you're interested later in that. And final thing we found out is that There are some remnants in our data which made our model to kind of converge into a super trivial solution, which we don't want. So this is one sentence that matches the extraction pattern, and I promise this is the last one you will see. So from there we have anaphoric sentence and antecedent. And as maybe you remember, I said that success at M measures whether the antecedent or a candidate that differs in one word is in the first M rank. So the way I coded this is I said, okay, all antecedents are in antecedent list. I put such candidates that differ in at most one word. But then when you do such a thing for silver cases, these candidates which differ from antecedent in exactly one word, like said here, and this word appears exactly before the anaphor, your model can just say, okay, great, I see said here and I see said in the beginning, so all such candidates will be ranked very highly, and because success at N rewards that, you would have a model which is really buggy but gives you a really good output.
So why is said maintained in the candidate? Wouldn't you want to strip that away when you?
So our measure measures whether the candidate or whether the antecedent or a candidate that differs in one word are in the first N rank. So just the way I coded it, I've already put this candidate in a list of positive examples. You can have them differently, of course. And then during the training, the max margin objective doesn't take only one positive example, but it takes few positive examples and takes the maximum score of one of them. So it has seen this candidate during the training as a positive example, which is a problem. So we had to remove this. And this is like a huge takeaway message, like you can have a really buggy model, but it can still give you right outputs. Okay, final thing we have done regarding our silver data, we try to make some pre-processing decisions to make it as much similar to gold data as possible in some core properties. So here now in ongoing work, we have this additional data set. This is the subset of the Connell 2012 shared task with events. And we parsed more from New York Times corpus. And now our development set is not only nominal, but nominal and pronominal. So we made some pre-processing decisions. And I think the most important one was to reduce the number of instances where the word that governs the head of the anaphors is says, saying, said, which was overly represented in our data. So that's why now this word state journal part gives us much less data, like 10 times less than we had before. And with this clean data, now you see nearly the same performance of nominal and pronominal part of our corpus, which is great because before we have difference in more than 10 plus S1 points. However, now we notice that great, our pronominal part is doing better, but Connell pronominal data set is not doing so well. And this raises some new questions because these are both gold and both pronominal, but the performance is there is a huge difference in performance. So what's going on there? But let me first answer the questions I already raised before. So should nominal and pronominal anaphors be learned independently? No, they should not. Great. Is harvested data noisy? It was very noisy, but it's clean now, and I think this was a major step to take. So we could have gone further with our experiments and maybe already train our model separately. So going back into our data and our implementations and checking what might have gone wrong was better decision to take. And finally, are natural and extracted data similar enough? Well, we took many measures to make them as similar as possible, but at the same time, we have noticed that even these naturally occurring data sets differ. And this made me wonder, are all properties of all type of abstract anaphors homogeneous enough? do we need specifically adapted training data for these events? Are these events, is it possible to even solve them using this relational model, or they are just not inherently relational? And the final and maybe the most important question is, well, how does this model performs in the realistic task setup, where we take sub-constituents from few preceding sentences, and not only from the sentence which contains the antecedent, which we continued to adapt from the prior work. So these are our ongoing challenges, and I would like to talk a bit more about them. So first, about this realistic task setup. So here, in this ongoing experiment, we take the 4 preceding sentences, and we take all S-like sub-constituents from there, and try to rank one of them with the highest rank. Prior work tells us, not prior but related, tells us, well, great, if you were going to do that, better think about the distance. Distance is an important feature. So how can we integrate the distance? Before coming to that, I want to just show you a few modifications of our model. First, because now we are just taking S-like constituents, not all constituents. This constituent tag label is unnecessary. And what we acknowledged is that, well, this verb that governs the head of the anaphor is a really good indicator of the relation between the antecedent and the anaphoric sentence. So we concatenate the embedding of the verb that governs the head of the anaphor. And I don't know why, but we kind of concatenated this additional hand-designed features at every LSTM step, which is kind of unnecessary. So now we have these 2 separate spaces, one for LSTM features and one for hand-designed features. And coming back to our question of how to integrate distance, well, we just concatenate the embedding of the distance, which we learned during the training, which is not so trivial because our harvested training silver data doesn't have natural distance. So once you take off this embedded sentence, it just doesn't, it just floats somewhere. So what we have done is we just sampled the distance from a count distribution calculated on our development set, which is natural. The problem is here is that our development set is consists only of shell nouns and events, whereas in the allow corpus you might have more than these 2 types. But nevertheless, we go further with this, and we want to tell more about differences between training on our silver data, training on a small scale gold data we have, and training on mixture. So we have a setup where we train only on silver, where we train only on small scale gold, and where we train for both of them, where once we sample a batch from silver, and once we sample the batch from the gold data. Okay, so now there are too many numbers here. I will try to recap quickly what is the outcome. First, we introduced a new evaluation measure, which is inspired by the work on a sentence compression. So here we are calculating how many tokens in the predicted antecedent occur in the real antecedent, and divided by the number of tokens of the predicted antecedent. That's our position, and recall is the same, just divided by the number of tokens in the antecedent. And in here, in every row, we have taken the window, which is the anaphoric sentence, and the preceding sentence. That means the +1, +2 is 2 preceding sentences, and so on. And in every of these rows, we have different number of examples we are evaluating. Here we are just evaluating examples in the corpus whose antecedent really is in this window. So the ones we have a chance to resolve anyway. And all I want to say here is that once you have more than one sentence, you have 2 sentence confounders, the model has a harder time. But if you add 3 or 4 sentences, its performance is not worse, it's actually better. So it profits for having more negative sentences. And you can see here that for pronominal cases, the drop is not so huge because their antecedent usually occurs in the previous sentence. Okay. If you compare what are benefits of our large-scale silver compared to our small-scale gold data. So here, when you look at this token F1, you can see that our training on silver data gives like a large improvement. But when you look at the success at 1 precision, you can see that, for example, here for nominal cases, it's not beneficial at all. So the outcome of this study is that training on silver data gives you better chance to, like, it gets the model better feeling where the antecedent is, but it doesn't give him the better ability to pick the exact right antecedent. But this is actually really nice because, as I said, even we as humans don't generally agree on the exact boundaries, so this is something we should care about more. And having mixed data helps a bit, but not so much. Okay, and having this new measure is great because now we have a better picture about this Conan data set as well. So here is what we had before with our precision success at 1. And the picture really looked a bit pessimistic. It seems like we are doing much worse for events. However, if we have this token F1, we see that we are doing worse for events, but not so much worse. So in the end, for events, we can point to, I don't know, like we can focus on the right place, but we are not picking the right antecedent. So in the end, these data sets are not horribly different, and I think we have a chance to resolve these events. But I think still, it's not crazy idea to wonder, like, are these just related tasks? And there is immense work on multitask learning, and I have worked on it, and some of you have worked too, which tells us, well, maybe you should keep some parts of this architecture specific to anaphora type. So what we could do is, instead of having this one scorer for everything, we can have 3 of them for at least 3 different data sets we have here, right? Our initial study showed that we compared only training on small-scale gold with 1 scorer and 2 scorers, 1 for events, 1 for shell nouns, showed that we don't have big improvements from multitask learning, but more experiments needs to be done when we take into account silver data. And another problem is that in Arab corpus, you can have events, shell nouns, or something third. So the question is which scorer to use. So maybe in the end, we will have to seek for a solution in learning-to-learn approaches or soft parameter sharing. Next, we wonder, are natural and extracted data similar enough? And maybe you wonder why are we still so worried about these data differences? Well, we did processing only using the ASN shell noun and conal events dataset, and in Aura we might have more. And harvest and the natural data may differ in some complex features we couldn't cover with our pre-processing decision. So we wonder, can we reduce these remaining complex biases with adversarial training? So here we added these 2 discriminators, one for LSTM features, one for hand design features. And these discriminators should predict on the basis of these features whether the current batch of data comes from silver or from gold. And what we want is that these features are invariant of the data type. So these discriminators should perform badly. So we want to maximize its loss. We want to change these parameters here such that here we have the maximum loss. However, these are too small machine learning systems, so we need to train them and we need to minimize that loss. So we have this min-max optimization, which is known as adversarial training. And the question is just how do we backpropagate here? So here we calculate the loss, we backpropagate normally, and then we have loss of our discriminators. We backpropagate again normally, but now we need to change these parameters of the LSTM such as that here we have the maximum loss. Or in other words, we need to move in the worst direction, and the worst direction is exactly opposite of the direction of the gradient. So here, instead of moving in direction with plus, you move in the direction with minus. And of course, this is just a question how to implement this. Here you have this switch. It turns out to be very easy. It's called gradient reversal layer, where you just implement, you have a class that implements a fifth overlayer to behave as identity, and then here in vector path it behaves like identity, but here as the negative. So it's literally just one more line of code. And same for the other discriminator. And our initial results show some benefit of this adversarial training, but they are really small, and the question is, are these just like variants of the model? And we need to see whether these results are significant. And if they are, it would be really interesting to see for which cases we benefit from this adversarial training. And final question is, well, we work a lot to learn these individual representations. And what I believe is that we benefit for our silver data to capture better lexical features, which have been shown to be very important for neural coreference resolution too. However, we have a better chance to learn such lexical features. So maybe we should listen to Sebastian, and he says that NLP's ImageNet moment has arrived. And instead of learning these representations from scratch, we can use a pre-trained language model such as Elmo, and we will probably capture probably have a much better similarity space where with these comparing this representation will yield a much better joint representation. So I don't have results of this yet, and I hope to tell you that very soon. Okay, this brings me to my final slide. So we have made a good step towards our goal, which is a unified unrestricted abstract anaphora resolution. We have a stable baseline neural model for core phenomena, and we learned how to integrate this harvested training data properly. However, there are serious challenges in front of us. We need to alleviate these divergences between our silver and HL data. We need to take care of these different abstract anaphora types, so we need to find how to leave some of parts of our architecture anaphora type specific. And finally, we need to select antecedent from the wider context. So the more we move forward, the steeper it gets. Thank you for your attention.